Hello, I'm Katie Emerald, and this is my final project presentation for the Harvard Extension Deep Learning class. This project investigates the use of physiological data collected from wearable medical devices to detect seizures for epilepsy patients. Machine learning techniques have powered groundbreaking achievements in this area of study. Recent advancements in wearable sensor devices have the potential to greatly improve the lives of epilepsy patients and their caregivers, with the ability to detect seizures outside of a clinical setting. This project explores building a deep learning model trained on a wearable device dataset for seizure detection. Around 1% of the global population is affected by epilepsy, a neurological condition that causes seizures. Epilepsy patients have a higher risk of accidents and mortality than the general population. The goal of this work is to build a model for seizure detection, allowing alerts to be sent to caregivers such that medical treatment can be provided as soon as possible. The ability to detect a seizure early can be life-saving. This project is based on the SeizeIT2 study, which includes a time series dataset collected with a sensor-wearable medical device from a company called Byteflies. The full dataset contains over 11,000 hours of wearable data for 125 patients with epilepsy. The physiological data are stored in binary files in the European data format, which are readable using the PyEDF-lib Python library. The dataset is organized according to the Brain Imaging Data Structure Standard. The dataset is available to download on OpenNeuro, a platform for sharing VIDS data. The dataset contains 4 types of modalities for each subject, also known as patient. The scope of the original study and this project only covers the EEG modality. EEG measures electrical activity in the brain, and this is the primary signal for detecting neurological electrical storms and is extremely useful for seizure detection. The sensor.device collects additional modalities that are also very useful for seizure detection. ECG can detect irregularities in the heart, EMG can detect dysfunctions in the nervous system, and MOV can detect irregular movements. These other modalities can be added for more sophisticated models and monitoring systems. These are the steps for the project at a high level, including pre-processing, metrics, model training, post-processing, and evaluation. Data engineering involves a significant amount of pre-processing to prepare the data for model training, as well as post-processing required to evaluate the model performance comprehensively. The training set and validation sets are split 80% to 20% and are organized by subject. The dataset organizers distributed the seizure events with the same proportions across the training and validation sets. EEG sensors record the electrical signals in the brain, characterized by amplitude in microvolts, frequency in hertz, and location, as well as many other properties. These measurements capture alpha, beta, theta, and delta waves of the brain to detect physiological state, such as awake, asleep, or activity. The data is loaded from EDF files and converted from binary into arrays. The EEG signals are extracted and stored into a list, and the sampling frequency and channel label are appended to lists respectively at the corresponding index. Events data are stored in the EEG modality directories corresponding to each subject, session, and run. The events.tsv file in each directory tracks the event onset, duration, event type, and other metadata. The annotation class loads and parses the events. Seizure events are extracted by checking the event type value and storing the onset and offset times. Non-seizure events are called background events. Matplotlib is used to render the waveform visualization, showing the EEG signal amplitude over time, along with event annotations to highlight the seizure period. Recordings are sampled into segments. A segment is a section of a full recording. A segment key is a reference to a recording with a start time, stop time, and label. This is done because the recordings are too long for the model to consume directly. There is significant class imbalance in the dataset. since there are many more background events than seizure events. To balance the two classes, the majority class samples are undersampled relative to the number of minority class samples by a factor of 5 based on the study. This happens during the sampling process while extracting segments from the recordings. EEG signals are resampled to 250 Hz and filtered with high-pass, low-pass, and notch filters. An individual signal is captured by a sensor and is streamed through a data channel. The channel label describes the type of channel in this dataset. It refers to the positioning on the head. The focal channels, left and right, are two sensors placed on the same side of the head, and the cross channel is the sensor on the opposite side of the head. A focal seizure is a type of seizure that occurs on one side of the brain only. Focal seizures are the main focus of this study, although patients who also experience other types of seizures were also included. Patients who have focal seizures had two sensors placed on the side where they usually have seizures, the focal channels left and right, and one sensor placed on the opposite side, the cross channel. In this study, only 2 of the 3 total channels are selected, either the left or right focal channel and the cross channel. Generators are used to preload the training and validation data for model training. Generators are essential for this project. Otherwise, model training would be extremely slow due to the amount of data and pre-processing involved. The custom segmented generator class extends the Keras utility sequence-based class, which is used to load large datasets dynamically in batches and supports multiprocessing. This base class has been renamed to PyData in Keras 3. This project leverages a combination of built-in metrics and custom metrics. Accuracy shows how often the model prediction matches the true value, although this metric is not super meaningful when training on imbalanced datasets. A seizure is relatively rare in this dataset, and the model could predict a background window all the time and still achieve high accuracy. Area under the curve of receiver operating characteristic measures the true positive rate versus the false positive rate. Area under the precision recall curve measures how well the model identifies the rare class in an unbalanced dataset. Precision shows what percentage of positive predictions were correct. Custom metrics functions are applied during training, validation, and post-processing evaluation. Specificity is known as the true negative rate. This shows how many negative predictions were classified correctly. A high specificity means few false alarms. When the model makes a negative prediction, it's almost always correct. Sensitivity is known as the true positive rate or recall. Sensitivity shows what percentage of actual positives were correctly classified as positive. A low sensitivity indicates a high number of false positives, meaning that the model is missing many positive predictions. This is an important metric for this use case and other healthcare use cases for disease prediction. Sensitivity shows the percentage of actual seizures that were detected by the model correctly. Focal loss is meaningful for imbalanced datasets. Focal loss adds a modulation factor to reduce the contribution to the loss value of easier to classify samples and increases the contribution of hard to classify samples. The SeizeIT2 study adds custom weighting to reduce the influence of the common background samples and adds more weight to the seizure samples. The ChronoNet model is a convolutional recurrent neural network designed for time series classification. The model is a stack of convolutional layers with normalization and dropout, where the outputs are then passed to a stack of recurrent layers. Convolutional layers detect patterns in the data and extract features with filters. Convolutional layers detect short-term local patterns in the time series data and can recognize those patterns across different time positions in the signal. The stacks are built with the inception approach, where increasing kernel sizes are applied to each layer and the block of layers and run in parallel and then concatenated together. Recurrent layers detect longer-term patterns in the data, keeping a running memory of past information. The gated recurrent units variant has gates to decide what to retain in the internal state. After the recurrent layers, a dense layer maps the final representation to the output class. The softmax layer then converts these values into probabilities to make sure the outputs sum up to 1, representing the confidence for the predicted classes. Window level metrics measure how well the model performs on the individual segments only in this case. Window level metrics are the statistics captured by the training and validation process in the output of the model, in this case with the restore best weights early stopping callback enabled. Good metrics at the window level show that the model has learned how to tell the difference between seizure and background segments. Performing well at this stage is an important starting point, but this approach will not show how well the model will be able to detect seizures within a continuous EEG signal in a real-world scenario. Window level evaluation also doesn't capture the false alarm rate, which is important to minimize for usability. With that said, it's still very important for the model to perform well at the window level, and it is a necessary prerequisite before proceeding to event level evaluation. This is because if the model can't distinguish between segments, then it certainly won't be able to perform well on entire events. The training and validation metrics appear to be an acceptable starting point. The loss is low, which is a good sign. The training accuracy is strong, and there is not much of a gap between the training and validation accuracy. The AUROC and AUPRC are strong as well, showing that the model is classifying the rare class well. Specificity is also strong. Most of the metrics except sensitivity have very little gap between the training and validation values, indicating that there is not an overfitting issue generally. The training sensitivity is high, but the validation sensitivity is much lower, indicating a gap in sensitivity. Additional research is required to identify the cause of this issue. In summary, most of the validation metrics look acceptable at the window level with the exception of sensitivity. Event level metrics will provide additional insight. Custom functions reassemble segments into events and calculate event level metrics based on the techniques shown in the SeizeIT2 study. Metrics are calculated at a range of threshold values. The threshold value is the probability that the prediction must be above for the event to be counted towards the metrics as a seizure event. At threshold 50%, a seizure probability above 50% will be evaluated as a seizure. Similar to the SeizeIT2 study, this project iterates through a list of thresholds from 10% to 90%, and the best result is chosen from those results. The SeizeIT2 study iterated through a wider range of thresholds and ultimately chose 50% as the best performing threshold. In this project, the best threshold also seems to be at 50%. This project's metrics generally look somewhat similar to the SeizeIT2 study results, with some improvements and some deficiencies. In this project, the AUROC and the AUPRC are higher, and the false alarm rates are significantly lower. So that's a good thing. Although the sensitivity is lower than the reference study, indicating an increased number of missed seizure events. According to the results shown in the range of thresholds, the threshold value could be adjusted down to 40% to increase the sensitivity, but that's at the expense of increased false alarms and decreased specificity. And here are some plots showing the curves for the results that we just reviewed. And that concludes my presentation. Thank you so much for watching, and let me know if there are any questions.